Now, you should ideally then be able to pick any two eigenvalues, write down the characteristic equation, then write down a whole series of matrices, probably starting with the most obvious one, but then going through a process similar to the one we used here, and finding a whole series of matrices, at least half a dozen, that give you the same eigenvalues. Pick one arbitrarily, or pick more than one, or work through these. Find your eigenvectors, do your T-matrix, columns of eigenvectors, do the similarity transform, and find, and actually do the calculation here and find that you come out with the same matrix you would have if you did this, the matrix with the eigenvalues on the diag. Okay, now, we're going to kind of transition our thinking, okay? We've got our y prime equals ay system, okay? That system, for the system that we're using, well, right here is the system that corresponds to that 5, -4, 3, -2 matrix. Now, this is the last thing we get to. Our flow of ideas here is going to go down through this and back up through all this stuff. So you'll understand this process and why diagonalization works. I got things a little out of sequence here, so let me. Okay, so if we have this would be this. So put a green circle around this. So that's really the same as this. Of course, we can solve this system using methods that we're used to using. Okay, but we have another way of solving it. So if I write the system in terms of a matrix, phi here is going to be a matrix solution to the equation phi prime equals a phi. Same equation, but now we're not talking about a column vector. We're not talking about a y1, y2 vector, where y1 and y2 are these functions. We're talking about just a matrix solution. And the point then is that just as the solution to a simple linear equation like y prime equals 5y, you solve that using an integration factor. And actually in that case, you just solve it by letting y equal ae to the lambda t, or to the rt, let's say, and evaluating r. Well, we should be able to do a similar thing here. We can let phi be e to the at, where a now is a matrix because we know how to do an exponential of a matrix, provided, well, okay, we know how to do the exponential of a matrix, provided the matrix is diagonalizable, and that's what we're going to do, okay? So we're going to just simply say that, well, the solution of this is phi equals e to the at, where a is this matrix. And of course, this is conditional on a being diagonalizable. Now we're going to use the A matrix that we have already derived for eigenvalues, lambda 1 equals 2, lambda 1 equals 1. Here's our matrix. Okay, we know it's diagonalizable because we just diagonalized it. Okay. But you see that as long as you have a diagonal matrix A, you can diagonalize it and do exactly what we're going to do with this one. Okay, so here's your A matrix. Okay, it diagonalizes to this. We know that already. We've worked that out before. And now we can do E to a diagonal matrix, as we've seen before. If you just do the Taylor expansion of the matrix, since every power of the matrix, of a diagonal matrix, is obtained just by doing powers of the numbers on the diagonal, it turns out E to the dt, if the diagonal is matrix is this, is just e to the 2t, e to the t. Okay, with your eigenvalues here and here. And we've been over that, so we've seen how that works. Okay, so the basic thing is, if you're given one of these, you diagonalize A, and you can find e to the dt, where D is the diagonalized matrix. And then you can inverse transform this back into a solution to your system, and that's what we're going to do. Okay, so, well, here's your inverse transform. Okay, remember now, to diagonalize this matrix, we did the TAT inverse on the A matrix. Now you know that when you do that and go through all the details, you can let y equal tz, and the z vector uncouples the matrix, or uncouples the system, so that you have a bunch of equations that can be solved using integrating factors, using just the methods of first order systems. We've been through all that. You should know how to do that. Now we're just kind of bypassing all that, because this matrix is invertible and has eigenvalues. We can do this. We can get the diagonal matrix. We can get the e to the dt, the exponential of the diagonal matrix multiplied by t, and that's what it's going to be. Eigenvalue here. Now we inverse transform, okay? Now to transform this matrix to this, we did T inverse times A times T. If we want to transform back, we got to do T times this diagonal matrix times T inverse. That's the inverse of the similarity transform. So we've essentially mapped this matrix into another basis where the matrix is diagonal. We've done something with it. Now we've got to map it back to the original basis. And that's what we do here. Okay, so that's why we do the T, e to the dt, T inverse. Now you can think about that more deeply, but that's how it works out. Okay, well, how does that work? Well, we just write it out. Here's our T matrix, here's the inverse of our T matrix, and here's our diagonal matrix. Yeah, we multiply it out. This multiplication is really easy. You should do it yourself. And then we multiply by this, and it's clear that this times this equals this. Now you should write that out yourself rather than try to look at it and see it, because you'll see it much better if you write it out, and you can write it out in an instant. You can stare at this for half an hour before you see the connections. If you write it out, you see them much more quickly. Okay. So, that's it. We've got this. Now what in the heck does it mean? Okay, well, let's talk about what this means. Then we'll interrupt the clip here, do that in another video, and interpret this in a way that illuminates the solution to this system.